Okay, we move on to worksheet number 4, and this is about this one is about topic 1.2, which is motion. But in this, we'll be doing theory questions related to mostly related to graphs of the motion. Okay, so interpreting and solving the graphs of motion. Okay, take a look at the first graph. A window cleaner drops a sponge from the balcony of a hotel at time t is equal to 0. Figure 1.1 is the speed time graph of the motion. So this is a speed time graph. Let's analyze the motion. The 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 sponge, somebody dropped a sponge from the floor. So the sponge accelerates uniformly, then the decreasing acceleration, and then reaches constant speed, and it comes to rest, decelerates. It the moment it drops, it comes to rest, and that's that. Okay. State the value of time t when the sponge is moving with uniform speed. What is the value of t? So this is the region basically where it is moving with a uniform speed, right? This is the region where it is moving with a uniform speed. So you can pick up any value of time. Ideally, pick up the middle value, the value of time, which is 2 seconds is the time where it is moving with a uniform speed, right? Why is my pencil slow? Moving with uniform speed, right? So you can pick any value of time. For example, I'll pick t is equal to 2 seconds, right? Accelerating at a non-uniform rate. So if you notice, initially it is accelerating uniformly, but this is the point somewhere at this point where this is accelerating non-uniformly. What is the half? What is the midpoint? What is the middle of between 1 and 1.5? You should do 1 plus 1.5 divided by 2, and you should get 1.25. Okay, this is the midpoint. So this value is should be 1.25. And the halfway between 1 and 1.5, it should be 1.25. So I'll take this value of time. This is the time where it's accelerating at a non-uniform rate, and the time is 1.25 seconds. Decelerating. Okay, of course, 2.5 is the time where it is decelerating because it's coming sharply downwards. And the graph is coming downwards. That's what we know that the something is decelerating. So t is equal to 2.5 is when it is decelerating. Okay, calculate the distance traveled by the sponge between t is equal to 0 and t is equal to 0.75. So if you go back to the graph, distance traveled, this is a speed time graph. We want to work out the distance traveled, which means we're looking for the area under the graph. Okay. So from 0 to 7.75, 0.75 should be over here. This is 0.75. I'm going to draw a line. Then this is the area of the graph. This is the area of the triangle that I want to find out. And if you notice, this is 6. I feel like this is 2, 3, 4, 5. So 2.5. At 2.5, it should be 7. Right. So what is this? At which point it is hitting? I believe it's hitting at this point, which is 1, 2, 3, 3.5, which is almost. I'm gonna take 7.1. You can take any value. I'm gonna take 7.1. Not any value. You can take a value that's close. Okay. So I'll calculate the distance traveled. So this is the triangle, a triangle that looks like this, that has a bottom of 0.75 and the height is 7.1. I'm so sorry. 7.1. 7.1. You should be able to read the graph. 7.1, right? So let's calculate the area of this triangle. 1 over 2 multiplied by 7.1 multiplied by 4.75. Let's work it out. 7.1 times 4.75. 7.1 multiplied by 0.75 divided by 2. I'm getting 2.66 meters. 2.66 meters should be your answer. Right, next. The graph shows us, figure 1.1 shows a speed time graph of a car. T is equal to 15 seconds, the brakes are applied, a car comes to rest with uniform deceleration. State the speed of the car just before the brakes are applied. So initially the car was moving at a certain speed, right? And initially the car was moving at a certain speed. And then, of course, at T is equal to 15, the brakes are applied and the car decelerated and came to rest at T is equal to 20. State the speed of the car just before the brakes are applied. So just before the brakes are applied, this is the speed of the car, which will be how much? 10. There are 10 boxes between 10 and 15. So every box should represent one number, which means every two boxes represent one number. So 11, this should be 12, this should be 13, this should be 14, and this should be 14. So a line that is between 11 and 12 should be 11.5. So this number over here should be 11.5. So the speed, when the brakes were applied, the speed of the car was 11.5 meters per second. State is when it's meant by uniform deceleration. Of course, we've seen this definition a couple of times. When there is unequal, because we're talking about uniform deceleration, right? So there should be equal decrease in speed in equal interval of time. That's when you say that there is a uniform deceleration. Take a look at this question. Figure 1.2 is a speed time graph for a motorcycle along the straight section of the track. Okay, so the graph starts at 40, which means initially the speed is 40. For time 0 to time 20, determine the acceleration of the motorcycle. So from time 0 to time 2 is here. At this point, what is the speed at this point? Let's see. Every box, 1565 lines in between, which means every line should represent 2 meters per second. So 52, 54, 56, 58, and 60. So a line that is through the middle should be 55. At this point, it should be 55. At this point, it should be 55, right? Right through the middle. And this is the time that is 2. So this is the area of the triangle. Sorry, this is the gradient of the triangle that I'm interested in because I want to work out the acceleration, right? So final speed is 55, initial speed is 40, and how much is the time taken? The time taken is from 0 to 2 seconds, so 2 seconds. I'm going to paste the values over here. Initially, the speed was 40, right? So U is equal to 40. Final speed, which is V, equals 55, and the time is 2 seconds, right? So acceleration should be equal to V minus U divided by T. In this case, 55 minus 40 divided by 2. 55 minus 40 would be 15 divided by 2, which should be equal to 7.5 meters per second square. Make sure you're putting the right units. Okay, let's move on to this one. Shows a speed time graph for a car traveling along a horizontal road. Mark and label a point where a car has non-uniform deceleration. Of course, this is the point. This is, so let's label the parts of the graph. I'm going to label it as point A, point B, point C, point D, and point E, right? So between A and B, the graph, this is a speed time graph, so it has a constant speed between A and B. Between B and C, it has constant deceleration. Constant deceleration. Between C to D, the graph has non-uniform deceleration, and that is a decreasing one. Non-uniform decreasing deceleration. And of course, D to E is when it is at rest. So mark the point where the car has non-uniform deceleration. That should be between C and D. Take any point between C and D. I'll take 6. 6 is the point where the car is non-uniform deceleration. So mark a point. We'll mark at, I'll put a cross over here. You can just label it, put a cross over here. And label as, you can also label it non-uniform deceleration. Calculate the deceleration of the car at 3 seconds. Deceleration of the car at time t equal to 3 seconds, which means at this seconds, I want to work out the deceleration at this point, right? If you remember, slope of the speed time graph gives acceleration or deceleration, right? Which means I can simply work out the slope of this straight line, this line, right? So what is the slope of this line? You can pick any 2 points on this line. I'm going to pick the points at the end, right? I'm going to call this point as x1 and y1. So this point is 2, 30, right? 2 and 30. And this point is 4, 25, right? So let's work out the slope of this point. 2, 30 and 4, 25. 25. Let me label this point as x1, y1. x1, and call this y1, x2, and y2. So slope will be equal to, we know the formula, y2 minus y1 divided by x2 minus x1, which would be y2 minus y1 would be 25 minus 30 divided by 4 minus 2. The 25 minus 30 would be negative 5 divided by 2. So this is going to be negative 2.5 meter per second square. Deceleration is negative 2.5 meter per second square. Because it already says deceleration, so I don't have to put a negative, I'll just put a positive. Okay, because it already says that it is deceleration. So deceleration and negative cannot come together. It's either a negative acceleration or a deceleration. That's that. Let's move on to the next question. Let's take a look at the next question. The next question says, a skier sets off from rest. So there's a skier who started from rest. When you start from rest, which means the initial velocity, u equals 0, accelerates uniformly. We just saw this question a while ago as well. Accelerates uniformly. So acceleration is 3.4 for 5 seconds. So time equals 5. Calculate the speed of the skier after 5 seconds. So we need to find out the final velocity. Right. We know acceleration equals v minus u divided by t. In this case, acceleration is 3.4. We need to find out the final velocity. Initial velocity is 0 divided by time is 5, right? V minus u would just be v. I will move, if I were to move 5 over to this side, that is going to be 3.4 multiplied by 5. V would be equal to 17 meters per second. So 17 meters per second. The answer is 17 meters per second. Okay. At 5 seconds, the skier stops accelerating and travels further 10 seconds at a constant speed. The question is, draw a speed time graph. So this is pretty simple. Accelerates uniformly. We know that whenever there's a uniform acceleration from time t is equal to 0, t is equal to 5, this is 6, right? So between 4, somewhere between 4 and 6, there should be a 5, right? So, and the final speed is 15, 16, 17. This should be 17, 15, 16, 17, this should be 17, right? So I'm going to mark my point over here. And uniform acceleration means I'm going to have to draw a straight line from this point to this point. Okay, in fact, I will do for this should be a 5, right? And at 17, I'm should I mark my point like this, and then I will draw a straight line up to this point. In fact, let me redraw the straight line. Uniform acceleration is a straight line, right? So this is a straight line. Cool. Okay. It travels on stop accelerating and travels at a 10 speed, further 10 seconds at a constant speed, which means from 5, if I were to add another 10 seconds to it, that's going to be 15. So 12, that is going to be 14, right? And 15 should be somewhere over here, right? So at a constant speed, it should be somewhere over here. And I'm going to have to draw a straight line because constancy represents a straight line up into this point. Make sense? So this is the part where there is uniform acceleration, and this is the point where it is constant speed. Cool, constant speed. Uniform acceleration for the first 5 seconds, and for the next 10 seconds, it is constant speed. Next, how the distance traveled by the skier can be determined by using a speed time graph. Of course, how do we determine the distance traveled? By working out the area under the graph of a speed time graph. Or you can say area under the curve. If it's a curve, area under the curve of a speed time graph. That's it. All right, moving on to the next question. A car accelerates from rest in a straight line, which means accelerating from rest, initial speed is equal to 0. During the first 14 seconds, time is equal to 14. Acceleration is uniform and it reaches a speed of 25 meters per second, which means the final speed is 25. Calculate the acceleration of the car. We know it's v minus u divided by t. V is 25, u is 0. So 25 minus 0 divided by time it took is 14. So 25 divided by 14, you will get something like 1.785 meters per second. Square, in fact, because this is acceleration. Okay, from the first 14 seconds, the speed of the car continues to increase, but the acceleration decreases. So decreasing acceleration, of course, if it's decreasing, that is going to be a non-uniform decreasing acceleration. From 70 seconds to 80 seconds after the start, the car moves at a constant speed of 55 meters per second. Draw a possible speed time of the graph. Okay, so I'll make a graph like this. From time and velocity. When time is 0, the velocity is 0, right? And when time is 10, when time is 14, the velocity is 25, right? So let me mark these 2 points. And if this region is uniform acceleration, because this region is uniform acceleration, I'm going to draw a straight line. So time is 0, 0. Let me make my first point over here. The second point would be time 14, velocity 25. Time 14, velocity 25. Velocity 25 should be, well, this is 30, between 20 and 40. 25 should be 22, 24, 26, 28, and 30. 22, 24, 25 should be somewhere over here in the middle of this line. Right, we'll do it very, very carefully. 25 should be 22, 24, 25 should be over here, right, in the middle of this line. And the time is 14, right? Will time 14 be? So this is 10, 12, 14, 16, 18, 20. So this is time of 14. So this is time 14 means I am going to mark my point over here. Okay, and I will draw a straight line between these 2 points because the acceleration is uniform. This is the region that has uniform acceleration. Okay, afterwards, the acceleration, uh, afterwards, there's a afterward, there is a decreasing acceleration. And from 70 seconds to 80 seconds, where is 70? 60, this is 70, and this is 80. So between 70 and 80, this is a constant speed of what? 55 meter per second. 55 should be, this should be 40, this should be 50. And 52, 54, 56, 58, and 60. So 51, 52, 54, 55 should be somewhere over here. Right? So from this point to this point onwards, there's a constant speed, and by constant speed, I mean there's going to be a straight line between these 2 points, like that. In between these two graphs, in between these two parts of the graph, there is a decreasing acceleration. So decreasing, how does decreasing acceleration look like? Non-uniform decreasing acceleration looks like this, right? So this is the line I will draw between these 2 points. I'll draw it very, very carefully. Oh no. Yeah, this is a decreasing acceleration. Okay, uniform acceleration. This is, I should write it with a better color. This is uniform acceleration. This is decreasing acceleration, and this is constant speed. So that's how you would draw the graph from the description. Okay, I hope it makes sense. You will score 2 marks for this drawing. Last question, on to the last question. Okay, this is pretty simple. A student drops a metal object into a cylinder of oil. The object falls alongside a vertical ruler, and the camera records its position at 1 second intervals. So at t is equal to 1, the graph is at, let me draw a table, t and d. Time is equal to 0. This is, distance is also equal to 0 because this is the initial time. And then time is equal to 1, the distance is 0.5 centimeters, right? Because this is right in the middle, 0.5 centimeters, right? At time 2, the distance is 1.5, 1.6. The distance is at 1.6 cm, 1.6 centimeters. At time 3, the distance is also 3 centimeters. At time 4, the distance is 5 centimeters. You can also see that. And at time 5, the distance is 7 centimeters. Okay, let's use this table to plot the distance. At time 0, the speed is 0, right? At time 1, the speed is 0. The distance is 0.5, my bad. 0.5 should be. So is this 0? 0.2, 0.4, 0.5 should be somewhere in between. So this should be 0.5. Then you have 1.6, so 1.2, 1.4, 1.6. At 2, it should be over here, 1.6. At 3, the distance is also 3, so 3 and 3, this should be over here. When time is 4, the distance is 5. When the time is 4, the distance is 5. This is 5. When time is 5, the distance is 7. So this is 7. I will connect all of these points very, very carefully. Do not connect it by using a straight line. Connect them by using a curved line. So we'll draw this very, very carefully. My tablet is a little slippery. Make sure that whenever you're drawing a curve, you are drawing it like this. Okay, let me draw this very, very carefully. This is the last question, so bear with me for like just 2 points. This and it goes all the way up to this, and this is what the graph would look like. Of course, you can tell this is acceleration because on a dt graph, if you have a line like this is acceleration. I hope it makes sense. I hope you're familiar with, I hope you're now better equipped to tackle theory questions on graphs of motion.